Okay, 7.4, vectors in 3D space. So we're going to look at vectors that not only act along the x and y axis, but in 3 dimensions, we can represent vectors using a third coordinate axis, which is the z-axis that you see here in my diagram. Okay, so we're going to look at vectors represented in 3D space. Now our coordinates for points will have 3 parts, 3 components to it, as well as our vectors. Okay. Now the way we're going to represent the axes are as follows. The z-axis will now be the vertical axis. The y-axis will be the horizontal axis. And you have to think of the x-axis as an axis that's kind of sticking out of the page. Okay. It's looking at the plane form. We have a YZ plane now made by the y and z axes, which will be kind of like our page. And if you look at the zx axis, it's kind of the red plane there, sticking out of the page. So x is sticking out positively, negatively be into the page, and z and y will be like our horizontal axes. Okay. So if we can make sense of that, then 3D vectors will become a lot more easier to understand. Okay. So how do we plot 3D vectors? So in a 3D Cartesian system, we now have points that are represented by ordered triples instead of pairs. So we have now x, y, and z. So x and y, just like 2D, are the first 2 parts of that triple. And this third component now we're going to throw in there is the z component. Okay, so to plot a point such as x1, y1, and z1, where x1, y1, and z1 are points or numbers, okay, we're going to look at moving x1 units along the x-axis, y1 units parallel to the y-axis, and z1 units parallel to the z-axis. So for points such as -1, -3, and 4, we're going to go -1, so along the x-axis, and then parallel to the y-axis, we're going to go -3, okay, and then parallel to the z-axis, we're going to go up 4 until we arrive at that point up there, and then we can, if we're going to represent this as a vector, you'd connect it from 0 to 4 as a vector, okay, but we're not in this case, we're just plotting a coordinate, all right, but what if we are going to draw vectors? If we're going to draw vectors, so that if we're going to say, hey, what is -1, -3, and 4, right? So then we're going to connect the origin to that point and draw that as a vector. I'll use a ruler for make that a straight line. There we go. So there's our vector in 3D space. Okay. So let's see. What do we have to do? What if we have to draw our own? So here we go. The first vector I'm going to draw is -2, 3, and -4. So I'm going to draw a set of axes here. Okay. Oops. Let's make them as straight as possible. Let's make that black. Like so. Okay. And maybe it's too long. Let's just make that a little bit shorter. Okay. And then we're going to draw. So that'll be our z-axis there. Okay, let's call that the z-axis. Let's draw. I'm going to draw it this way, so maybe it's easier to see using this kind of special grid where I'll have the y-axis this way and then the x-axis this way. So y and x. Okay, so the way this is going to work is if I'm going to go -2 along the x, well, if the origin's right here where the 3 axes meet, then -2 would be, sort of this way. Okay, so I'm going to start there. Let me zoom in there. Okay, and then I'm going to read the next component. That's a 3, so +3. So I'm going to go parallel to the y-axis 3 units. So, okay, 1, 2, 3. Right about there. Okay, and each unit is worth 1 unit, so each grid square is 1 unit, so that's what I'm following here. And then along the z-axis -4, so parallel to the z-axis I'm going to go -4, so I'm going to go down 4 instead of up. So 1, 2, 3, 4 until I end up there. So that point right there is -2, 3, and 4. And then if I want to draw the vector, I'm just going to connect the origin to that point. And here we go. And there's my vector. So it takes a little bit of an imagination to kind of imagine that in 3D space. So being behind the ZY plane and then pointing downward. Okay, so that's that vector. So vector -2, 3, and 4. And just like 2D vectors, I could take this vector and move it anywhere in 3D space, right? And it's still the same vector, okay? All right, so let's look at another one. What about 2, -3, and 1? Okay, so this one, let's do this in a little bit of a different color. So 2 along the x-axis, I'm going to go right here, 2 along the x-axis, and then it's going to go -3 along the y-axis. I'm going to be parallel to the y, but I'm going to go minus direction this time, so backwards. 1, 2. Let's use dotted lines here. So 1, 2, 3. Plot that point. Okay, and then +1 along the z-axis. So I'm going to go up 1. So I'm going to end up there. So I can draw the 3D vector from the origin to that final point, like so. And so there's my vector. We call that 2, -3, and 1. Okay, so it's just a matter of going along the x-axis and parallel to the y-axis, and then along the z, parallel to the z-axis. So going to the left for the x, along this way for the y, and then up or down for the z. Okay, and then you connect from the origin to the endpoint, and there's your vector. Okay, if I erase the guiding lines, you don't necessarily need the guiding lines afterwards. You can erase those, and then whoops. Then you should see, okay, we'll get a more clear picture of the vector that we have. Okay, so those are our vectors in 3D space. Okay, let's have a look at the magnitude of a Cartesian vector. So what's the magnitude of a Cartesian vector in 3D space? In 2D space, we know it was a Pythagorean theorem, the two components, the xy components. If you recall, xy components like this. If you had a vector, you'd have the x component and the y component, right? So x component, y component are the legs of this triangle, the right angle triangle, which you can use the Pythagorean theorem to find the magnitude of the vector. Okay, and that was your magnitude. In 3D, right? In 3D space, the magnitude of the vector is very similar, right? So let's start with this diagram here. If I had the vector u, which is just connecting the origin to some point P, okay, and the P is labeled ABC, the 3 coordinates, x, y, z, okay, I can say, well, that vector u can be created by creating a right angle triangle, by dropping the head of vector u down to a xy plane. Imagine the xy plane being a piece of paper. If I drop a perpendicular down to that paper, I would have one vector there, right? Vector OR to P. And along that piece of paper, the XY plane paper, I can create a vector from O to R, okay? And those two vectors would be 90 degrees to each other. Although it doesn't look like it here, you have to imagine it in a 3D space. Okay, so O to R, R to P are 90 degrees to each other, and that forms a right angle triangle from which you can use the Pythagorean theorem. So U squared is equal to the magnitude of the vector from R to P squared plus the magnitude of the vector from O to R squared, right? So O to R and R to P. And then you can further break this down, right? So what if I said, instead of R to P, what's a parallel vector to that? Well, I have one of these vectors here that lies along the z-axis. R to P is parallel to the z-axis because I said I dropped a perpendicular, and that perpendicular line will be, well, z is perpendicular to both x and y. So that is going to be an equivalent vector. So from O to S, instead of R to P, I'm going to replace that with O to S, okay? And that's that. And O to R, we'll keep that as O to R for now, right? But on my next line, I'll keep O to S, but O to R, this line, this vector right here can be rewritten as the vector from O to T. So let's put point T right there, okay? Plus T to R, right? And these two are 90 degrees to each other, Okay. So the vector along the y-axis and then parallel to the x-axis, x and y-axes are 90 degrees to each other. So that's a 90-degree triangle right there. So the triangle I'm talking about is this one right here. And so O to R becomes the hypotenuse of that triangle, and its legs are O to T and T to R. Okay. And then T to R, well, what's equivalent vector to that? It would be the vector here along the x-axis, because this T to R is parallel to the x-axis. So O to Q would be the equivalent vector. So I can replace T to R with O to Q. And now I have three vectors, OS, OT, and O to Q, which are vectors that are along the axes. Okay, so I can replace them now by saying, well, z squared plus y squared plus x squared. And there you have the kind of like our Pythagorean theorem in 3 dimensions. Okay, so I can say the vector u, or vector O to P, the magnitude of that is just the square root of x squared plus y squared plus z squared. So that's going to be an important formula for us to determine magnitudes of vectors in 3D space. Okay, and the same manner we did, we can state that for any coordinate points A and B, we can generate the vector from those points by subtracting b1 minus a1, the x component, b2 minus a2, their y components, and b3 minus a3, their z components. So we've been doing this for 2D vectors. We're just now adding a z component in there, and we're going to do the same thing. Okay, so I can create a vector a to b by joining 2 points here and then just subtracting their components. And magnitudes would be kind of like this Pythagorean theorem, but now for including a z component in there. So let's do some of that work as an example. So if I'm given 2 coordinate points, can I find the magnitude of A to B? So I can start by saying, well, yeah, I'm going to find the vector A to B. Okay, and vector A to B is just equal to the components. So B minus A, right? Just think of the second point minus the first point, each of their components. So B, 4, take away the x component of A, take away -2, comma, the y components, B is -3, take away the y component of A, which is 4, and Z for B is 5, take away the Z component of A, which is 6, and then I simplify. And if I simplify, I get 4 minus -2, which is +6, minus 3 take away 4 is -7, and 5 minus 6 is -1. So there I have my vector A to B, or vector AB. The magnitude of AB will then be the square root of the component squared, 6 squared plus -7 squared plus -1 squared, right? Just like the formula up here, right? So if I have each of their components, right, x, y, z, they are here, x, y, and z, and you just square each one and then take the square root. So here we have 6 squared plus, which is 36, and 7 squared minus 7 times -7 is 49, so plus 49, and 1 squared is 1. The square root of that, 49 plus 1 plus 36, is 86, the square root of 86, and you can leave it in this exact form. Okay, so that's how we calculate that. Let's look at the next part, operations in 3D space. So like operations we did in 2D space, the same applies to 3D space. So just now adding the Z component in addition to the X and Y components we're already used to from 7.1, 7.2, and 7.3. Okay. So if I'm subtracting, or if I'm adding or subtracting 2 vectors like in this first example, so let A be this 3D vector and B be this other 3D vector, I can subtract A, take away B by subtracting each of their components, right? So A take away B is just like in the 2-dimensional case, we just subtracted the X components, so -1 take away 4. So A comes first, and then B, so it's A take away B. And then the y component, so the y component of A is 2, take away the y component of B, which is -5. And now we have a z component to include here. So the z component of A is 3. Take away the z component of B, which is 6. Okay, and then we simplify. And the simplification gives us -5 and 7 for the y component and -3 for the z component. And there you go. Okay, there is A minus B. What if we had scalar multiplication? Same thing, we just now have a third component, right? So what is 3A? So 3 times vector A would just be taking all the components of vector A and multiplying them by 3. So we have -3, 6, and 9. And 4 times vector B would just be taking vector B, here it is, 4, -5, and 6, and multiplying them by 4. So 4 times 4 is 16, -5 times 4 is -20, and 6 times 4 is +24. Now, if we're going to add both vectors together, 3A plus 4B, I'm just going to be adding their components, right? So the x components are going to be -3 plus 16. The y components will be 6 plus -20. And the z components are 9 plus 24. Altogether, we have 13 for the x, minus 14 for the y, and 33 for the z component. And there you go. That's the answer. Okay. And so 3D vectors, when you add the vectors, subtract the vectors, the result is still a vector. Okay, so remember that. What about unit vectors? Well, we're going to now include a third unit vector k. Okay, k is defined to be the z-axis unit vector. So we're already familiar with I and j. Right? I is the x component, j is the y component. Now we're just going to include k as the z component. So any 3D Cartesian vector written in the square brackets form, a, b, c, can be written also as a sum of the unit vectors, the scalar multiples of the unit vectors I, j, and k. So we can say whatever you have for the components in the algebraic form now become the kind of coefficients of I and j and k. Okay, so let's look at do I have an example? Right. Okay, so let's add I, j, and k. Well, okay, for adding I, j, and k, if I wanted to put this in kind of algebraic form, what we're saying here is we're doing 1, 0, 0, plus 0, 1, 0, and plus 0, 0, 1. So if you add all of their components together, the x components 1 plus 0 plus 0 is 1, 0 plus 1 plus 0 is 1, and 0 plus 0 plus 1 is 1. So 1, 1, 1 would be the 3D vector when you add those three together. Okay. The you try questions, have a look at these questions, and we'll probably take them up in class when we see each other again. Okay. Let's have a look. So pause the video, try those questions out, and then we'll move on. Okay, hopefully you had a chance to do those questions. Save them as we're probably going to take them up when we get back to class. The next part here, two vectors are collinear if one can be expressed as a scalar multiple of the other, right? So let's talk about some new concept here. Two vectors are collinear, right? Meaning if one vector can be expressed as a scalar multiple of the other. So if I had a vector, right, and one was and I had a second vector, if the second vector was collinear, that means I could take, let's say this is vector A and this is vector B. I can say vector B is some scalar multiple of A because they act in the same direction, they act along the same line. Or they could be acting in opposite directions if it was a negative scalar. But yeah, as long as they're acting along the same line, then you would say they are collinear, right? So this is the same line, parallel to this one. Okay. So can that work? Well, it would be true if and only if that each of these components have the same scalar multiple, right? So if I looked at comparing the components, so compare the components, the ratios, right? The ratios. Let's look at the ratios. So if I look at the ratios of the x component, I have 15 over -10. What about the y components? Negative 18 over 12, okay? And the z component, negative 12 over 8. Are they the same ratio, right? So 15 over 10, I can reduce that to a negative 3 over 2, divide the top and bottom by 5. 18 over 12, I divide the top and bottom by 6. That is also negative 3 over 2, okay? And negative 12 over 8. If I divide the top and bottom by 4, I'll also have negative 3 over 2. So they are the same. They're all proportional to each other by a factor of negative 3 over 2. So I can say here that vector v equals negative 3 over 2 times vector u. Okay, so if one is a scalar multiple of the other, then yeah, they are collinear. Okay, now if one of these components happens to be of a different proportion, so if they were not all proportional to each other, if one of them was off, even the same denominator or numerator, then they would not be scalar multiples of each other, right? They would be actually pointing in different directions. So watch out. All components must be the same scalar multiple. Okay. So here's another example. Let's see. What if we want to get two vectors to be collinear? What would the components have to be? If you're given some of these components, but you have to fill in a and b. So vector u is negative 9, a and 15, and vector v is b, 2, and negative 5. So I want the x components, negative 9 over b, to be equal to the y components, a over 2, to be equal to the z components, 15 over negative 5. So 15 over negative 5 tells me, yeah, whatever a and b are, when I divide them, I have to get negative 3. So negative 9 divided by what gives me negative 3? Well, that would be just 3, okay? And what number divided by 2 gives me negative 3? Well, that would be negative 6. So if I made a to be negative 6 and b to be 3, then I'll have collinear vectors. So u and v are collinear if a equals negative 6 and b equals 3. Okay, so that's how we do that kind of a question. Okay, so let's look at what if two vectors are coplanar. Okay, so recall from our last unit that if you had two non-collinear, non-zero vectors, they can define any other vector on a 2D plane, right? So what we can say more succinctly is that any two non-linear collinear vectors and non-zero vectors can define a plane, right? This is true even in 3D space. So for example, if I had two vectors on a 2D plane, here's vector A and B. Again, we use the kind of parallelogram example, but you can extend the parallelogram infinitely, right? The entire plane, the entire surface of your screen is a 2D plane. And I'm saying that you can create, if I can take A and B and create scalar multiples of A and B, I can create any other vector in my 2D plane. So if I can do that, then essentially A and B both can define the entire plane, right? Because I can create any vector on that plane just using A and B, as long as A and B are non-zero and non-collinear, meaning they're pointing in different directions, not along the same line. Okay. So we come back to this formula that we did in the past couple of sections. Some vector W in this 2D plane can be defined by some scalar multiple of u and some scalar multiple of v, if u and v are those non-collinear vectors. So instead of A and B, I could say u and v. Whatever, just two vectors that are non-collinear and non-zero. So if that's the case, then we would say that all three vectors W, U, and V would be coplanar. They lie along the same plane. Okay, so if I had vector W here, these three lie on the same plane. But the moment I have something that's coming out of the screen, then whatever vector that would not be coplanar anymore with U and V or A and B. Okay, so we're looking at vectors that are all on the same plane. So imagine drawing 3 vectors on a sheet of paper. That sheet of paper is a plane. But if I stick a hole in the paper and put a pencil through it, and that pencil is another vector, well, that would not be a coplanar vector with the others. Okay, so if we're given 3 vectors in 3D space, yeah, these vectors can point in all sorts of directions, but can they be coplanar? Can I put all 3 of them lying flat on a piece of paper, or will one of them jut out? Okay, that's the question we're trying to answer, right? So we could have, so like, imagine a piece of paper. We have 3 vectors. Are they all on the same plane, or does kind of one of them stick out, right? Boom, out of the paper, right? 90 degrees to the kind of paper here. So if one of those vectors juts out, then it's not coplanar anymore. Right? So how do you figure that out? Well, then we have to say, well, C, vector C would be equal to some scalar multiple of A plus some scalar multiple of B, right? And so if I plug in my algebraic vectors here, I would have to say here, and wait, and it doesn't have to be C equals A plus B. It could be B equals some scalar multiple of A plus some scalar multiple of C. It doesn't matter the order. I'm just keeping it, somewhat familiar. A, B come first. So let's do the scalar multiples of A and B equal to vector C. So can we do that? Okay, so can 5, 0, and -1 equal to some scalar multiple of -1, 4, and -7 plus t times 2, -3, and 5. And the trick to solving this is to create what we're going to call parametric equations. Okay, parametric equations, where we break apart the vector. This is so what we see right now is kind of like our vector form. Okay, what I want to turn it into is parametric form. And parametric form means I'm going to take each of these components, x, y, and z, and break them up into those equations. So I'm going to have 3 equations, with one equation representing x, one equation representing the y, and one equation representing the z components. So if I took apart the x components, what are the x components? I got 5 in that vector, -1 in this one here, and a 2 in that vector there. So if I pull those apart, I can say, well, for the x component, I'm going to have 5 equals -1s plus 2t. Okay. For the y component, I can have 0 equals 4s minus 3t. And for the z component, I can have -1 equals -7s plus 5t. So why don't I highlight these? This is the x component. I'll do the y component in blue. So those are the those are the y components of my vectors. And then the remaining one would be the z components. Okay. So how does that help? Now, if I can solve, let's say I try and solve these pair of equations for s and t. It's a linear system, 2 equations, 2 unknowns. And then if I find s and t, so find s and t, and once I do that, I should be able to use s and t in the third equation. If it works, then I know that these 3 vectors are all coplanar, because I can find a scalar multiple s and t that works for all 3 components. Okay. Okay, so let's do that. Let's do that work. So let's solve the first 2 equations, the yellow and blue equation. So I'm going to write here, what if I multiply the first equation by 4? So if I do that, 20 equals -4s plus 8t. And then I rewrite the second equation, 0 equals 4s minus 3t. And if I eliminate s by by adding both equations, -4s plus 4s is 0. And so remember, what I'm doing is just modifying the first equation, thereby multiplying by 4 and leaving the second equation alone. Okay. So 20 plus 0 is 20. minus 4s plus 4s is 0, and then 8 plus minus 3t is 5t. And if I solve for t, I get t equals 20 divided by 5, which is 4. So t equals 4. What about s? So if I took the second equation, 0 equals 4s minus 3 times t, and now we know t is 4. Solve for s. So s is going to equal, well, for it's 3 times 4 is 12. Bring that over to the other side. So 12. 4s equals 12. So s equals 12 over 4, which is 3. So t equals 4 and s equals 3. We found s and t, but it has to work for the z component. Okay, so we're going to check the z component. So -1 equals minus 7s, where s is 3, and then plus 5t, where t is equal to 4. Does it work out? On the right side, we have -7 times 3, which is -21. 5 times 4 is 20. -21 plus 20 is -1, which is the left side as well. So left side equals right side. Therefore, yes, the answer is yes. The 3 vectors are coplanar. Okay. And maybe when we get back to the class, I'll have an opportunity to just kind of show you that visually. I'm going to take out, you can take out GeoGebra. If you're familiar with GeoGebra, you can try and plot them. But if not, I will take the time to show that to you. Okay, so here are the 3 vectors drawn in GeoGebra. Okay, so we have vector A over here, -147, and vector B, 2, -3 and 5, and vector C, 5, 0, -1. Okay, now it's like, well, do you see that they all 3 can form a plane? Now, the plane is not going to be exactly on an XY plane or YZ plane, right? In fact, it creates a plane on its own, right? So if I show you the plane, boom, this is the plane. Okay, maybe it's easier to see this way. So you can see all the vectors line up on that plane. Okay, so those 3 vectors make a plane. But the moment you change one of the vectors, let's say vector C, instead of a -1 at the end, let's say you make it a 10, right? Notice how, whoop, that vector is now off the plane, right? So those 3 vectors will no longer make would no longer be coplanar just because of that one change. So that's why it's often you have to be checking all 3 components, x, y, and z, to make sure that that you can determine if they are coplanar. Okay. Okay. Back to this. So equations 1, 2, and 3 that we have all here, the x, y, and z component forms a system of equations, each with 2 variables. So technically, we have a system of 3 linear equations with 2 variables. And since we found a solution for s and t, then we can call this system what we call consistent, because there is a solution. If there was no solution, the system would be inconsistent. And we're going to come across inconsistent systems as we go through the tail end of this chapter. Okay. All right, what about dot products? We did dot product in 7.3. What about dot product in 3D space? So we define the dot product of 2 vectors in 2D space in both geometric and algebraic form. The development of each is similar to vectors in 3D space. So for vectors in 3D space, the formula is the same, right? Except the magnitudes of A and B now use that with the kind of modified Pythagorean theorem with a third component, the z component. So we have to keep that in mind. So remember, magnitude of A now would be the square roots of, the x component squared plus the y component squared plus the z component squared when you're dealing with 3D vectors, okay? But other than that, the dot product formula for geometrically is the same. Algebraically, however, it's one change, and because as you can imagine, it's just the addition of a z component here, right? So the product of the x components plus the product of the y components plus the product of the z components. So now we're saying vector A is defined by the components A1, A2, and A3, and vector B is defined by the components B1, B2, and 3. Okay, so that is just now what it looks like for a 3D vector. Okay, so if we're given two vectors now with x, y, and z components, how do we find the dot product? Just take the components, the product of each components, and add them together. So for u dot v, I'm going to take the x components of each vector, -8 and -2, and multiply them. So -8, -2, multiply 3 and 7 and add it together with that. So 3 times 7. And then the z components, 5 and 3. Okay, then you add them up. 8 times 2 is 16, 3 times 7 is 21, and 5 times 3 is 15, and that equals 52. Okay, 52. Is that 36, 46? Yeah, 52. That works. Okay, so there's our dot product. Okay, let's look at another example. What if we want to find the angle between these two vectors in 3D space? So they can have an angle, right? There's an angle between two vectors. That angle doesn't have to lie on an xy plane or yz plane. It could be anywhere in 3D space if those two vectors are pointing somewhere. Okay, so the angle, think about the angle for the geometric formula. It's still just rearranged for cosine theta. So if I rearrange for cosine theta equals, in this case, instead of a and b, we're going to use vectors u and v. So u dot v over the magnitude of u times the magnitude of v. All right, let me just see how much, we have lots of space here. Okay, so let's look at the magnitude of u, right? So that's going to be the square roots of all of its components squared. So -8, 3, and 5. So -8 squared plus 3 squared, the y component plus 5 squared, okay? And that's equal to 64 plus 9 plus 25, all square rooted. And 64 plus 9 plus 25 is 98, the square root of 98. And I can do the same thing for the magnitude of v. So that's going to be the square root of, let's look at v again, -2, 7, and 3. Okay, so -2 squared plus 7 squared plus 3 squared equals, let's see, 4 plus 7 times 7 is 49, 3 squared is 9, that's going to be 62, the square root of 62. So there we have it. We have our magnitudes, leave them in exact form. And so when I plug them into my cosine formula, cosine theta equals u dot v, which we already calculated here to be 52. Okay, so 52 goes on top, divided by the magnitudes on the bottom. So the square root of 98 times the square root of 62 equals, let's go, theta equals cosine inverse, putting all of that in there, 52 over the square root of 98, square root of 62. Now take out a calculator, do this calculation, make sure you can get it. Okay, divided by the square root 98 and square root of 62. Okay, cosine inverse, oops, just give me a moment here. So the answer here should be 48.2 if we round that. Okay, 48.2 degrees. So the angle between these two vectors, u and v, is 48.2 degrees. Okay, and so what I wanted to show you here is that here are the two vectors for u and v. Sorry, they're labeled u and v, but these are the two vectors. The angle we're looking for is that angle that's between the two vectors. So that's what we were calculating there. Okay, so it doesn't have, the angle doesn't have to be on the x, y, or z axes or those planes. It's just the angle between these two vectors in 3D space, right in the middle of 3D space somewhere. There's an angle between those two vectors. Okay, and then again, that angle we calculated is 48.2 degrees. So let's look at another problem, last one. What if we are solving a question like this? So here we have a triangle ABC. It has vertices of A, B, and C in coordinate form. These are not vectors, these are coordinates. Can we find angle CAB, meaning the angle between, formed by joining from C to A to B, so in other words, angle A. Can we find that angle? Very similar process to the previous question. However, I still have to create the vectors. Okay. So if just for a moment, just draw, imagine a triangle we need to draw here. So here's a triangle ABC, right? So A, B, and C, and there's some angle here you have to find, angle A, right? The angle created by joining from point C to point A to point B. That's what this means if you forgot how to read this. Angle joined from point C to point A, point C to point A to point B. So it's really the middle letter A, angle A. I want to find that angle. So I have to create some vectors here. I'm going to create the vector AB. So the vector joining point A to point B, right? And to get that vector, you just have to kind of, do B minus A, the components of B minus the components of A. So -1 take away 2. Those are the x components. These are the x components. Look at the y components. We have -3 and -4. So it's going to be -4 take away -3. And now the z components, 5 take away 4. And then when we simplify that, we get -3, -1, and 1. So that's vector A to B, right? Just joining those coordinate points, subtracting the difference between them, like rise over run, x and y, but now we have a z in there as well, and it's the same process. You subtract the z components, 5 minus 4. And then we're going to create the vector. So that's in our diagram. We have vector A to B, and then vector A to C. We're going to create that. Okay, so vector A to C. Similar idea, just subtract the components. So 3 for C, take away A, 2 is A, and then the y components, 4, take away -3, and the z components, 3, take away 4. Okay, and then we get 1, 7, and -1. Okay. Okay, so what about the third vector, B to C? Do I need that? Not for this part, okay? So, but because the second part of the question has find a vector that is orthogonal to vector BC, I'm just going to find BC anyways. Okay, so vector BC would be, so the coordinate of C minus the coordinate of B, so 3 take away -1. The y components are 4 take away -4, and the z components are 3 take away 5. And then we have, so simplifying that, we get 4, 8, and -2. Okay. Now, all we need is just these two vectors, A and B and A and C, for the first part of the question, because I want to find the angle between those two vectors. And remember, that's what the dot product is. The dot product takes two vectors and you get the angle between them, and you can find the dot product, that scalar product. So let's write out the dot product here. Vector joining A to B dotted with the vector joining A to C is just equal to the magnitude of AB times the magnitude of AC times the cosine of the angle between them. And what we're trying to find is that angle. What is the angle CAB, right? What is that angle between these two vectors, AC and AB? Okay. Now, do I have the dot product? Well, I could find the algebraic dot product because I have the algebraic vectors now. Do I have their magnitudes? Well, I could find the magnitudes. So the magnitude of AB is just the square root of -3 squared plus -1 squared plus 1 squared. So all I'm doing is taking these components, x, y, and z, squaring them, taking the square root, just like that kind of what I was showing you earlier with 3D vectors, the magnitudes of 3D vectors. So here they are, 3 squared is 9, 1 squared is 1, 1 squared is 1, so that's a square root of 11. And I could do the same thing for the magnitude of vector A to C, which is the square root of the squares, of sum of the squares of these components, 1, 7, and -1. So 1 squared plus 7 squared plus -1 squared, which is the square root of 1 plus 49 plus 1, which is 51. So there are the magnitudes. Let's take the dot product formula. and find the algebraic dot product. So AB dotted with AC equals, now we're going to find the products of each components and add them up. So the x components are -3 and 1, plus the y components are -1 and 7, and plus the z components 1 and -1. All of that together is -3 minus 7, which is -10, minus 1, which is -11. And then we can take these three values, the square root of 11, square root of 51, and -11, and put them into our formula for the dot product and solve for theta. Okay, so cosine theta equals negative. Okay, let's rearrange the formula first before I plug in the values, right? So the formula then, if I rearrange, it would be AB dotted with AC, moving the magnitudes over to the other side. So the magnitude of AB times the magnitude of AC. Okay, plugging in the values, I got -11 for the dot product divided by the square root of 11 and the square root of 51. And then if you solve for theta, theta is the inverse cosine of all of that. -11 over root 11 times root 51. And make sure you calculate this carefully in your calculator. The resulting angle should be 117.6 degrees, rounded, or 0.7 actually. Okay, so it's important to keep the exact value. Use square root of 11, use square root of 51. Don't calculate the decimal, don't round the decimal from these numbers until you finally get to the final answer. Okay. Let's go to the last part of this question. Find a vector that is orthogonal to vector BC. Orthogonal is just another word for perpendicular, right? Acting at 90-degree angles to each other. So if I have vector BC, I need another vector that's perpendicular, right? And so the dot product helps us with that. If you remember, the key thing about the dot product is that if I have two vectors, right? Remember, if I had two vectors, A and B, A dotted with B, they equal 0 if vector A is perpendicular with vector B. And we use this upside down capital T to represent something that's perpendicular to each other. So if A is perpendicular to vector B, then the dot product is 0. That's always true, right? Because why is that true? Because of the cosine, right? The cosine theta, if cosine is 90 degrees, if theta is 90 degrees, then cosine of 90 is 0. And no matter how big the magnitudes are for the vectors, cosine 0 is still multiplication by 0. Okay, so what I'm trying to do here is find a vector. Let's call it vector n, right? Find a vector. Let's call that vector n. And if I dot it with vector BC, the dot product must be 0, right? That's how I will know that the two vectors are perpendicular. So if I write where's vector BC? We said it's 4, 8, and -2. So I need a vector such that if I had n1, n2, n3, the components of vector n, dotted with, what were the components of BC again? They are 4, 8, and -2. So 4, 8, and -2. I want that equal to 0. Okay. So since these are algebraic vectors, if I did this 4 times n1 plus 8 times n2 minus 2 times n3, right? The x components being multiplied plus the y components being multiplied plus the z components being multiplied. It doesn't matter that I don't have an actual number for n's yet. I can still multiply the components and add them, right? So x, right, this is just the x, this is the y, and that's the z. Okay. And if they're going to be perpendicular to each other, the dot product must be 0. So the question is, I have one equation with 3 unknowns. What do I put for n1, n2, and n3? And it turns out there's many possibilities, right? So I could put numbers such as, let's see, 4 times 1 plus 8 times 1. What does that make? 4 plus 8 is 12, right? Minus 2 times what number makes 12? Well, if I put 6, so minus 2 times 6 is 12. Well, that will give me 0. So one possibility, one possible vector for n would be, well, if I made n equal to 1, 1, 6, then I would have a vector that's perpendicular to BC, right? And so it turns out that there's many other possible vectors, right? So like, here, if this is BC, right, you can have a perpendicular vector this way, okay, perpendicular. And now this is on a 2D plane. Imagine a 3D space, right? Like you could twist this around and create all sorts of different vectors pointing in different directions. Okay, so the possible vector is 116, but in a question like this, there could be another answer you could put too. It's essentially a trial and error type of question until you find a vector that gives you a 0 dot product. Okay, so that's kind of like the whole lesson, just looking at 3D vectors, right? Recapping everything we did, looked at how do you represent a vector in 3D space, right? Back all the way up here. How to represent a vector in 3D space. How do we how do you find the magnitudes of that vector? How do you write the vector algebraically given coordinates? And then how to do our operations on vectors, adding and subtracting and scalar multiplication, unit vectors. Okay, so everything we did in 7.1, 7.2, 7.3 all comes back here again, repeats again here, but now with a third dimension. Okay. And then we talked about how three vectors can make a plane. How can they be coplanar? Okay. And then we looked at the dot product, right? So applying the dot product in 3D space. So that is 3D vectors in our video lesson here. Okay, so please make sure you complete the notes, have a look at the practice problems that are assigned from the Google Classroom Word document, and come to the next class with questions. All right, that's it.